Dear students, welcome back to Blackboard. Today we are going to continue the part 2 of real numbers, Euclid's division lemma. Show that every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1 where q is some integer. We need to show every positive even integer is of the form 2q and every positive odd integer is of the form 2q plus 1. Solution. Let a be any positive integer and b equal to 2. Here we selected b equal to 2 because it is given here 2q and 2q plus 1. So we are going to apply the Euclid's division lemma here. Euclid's division lemma is for any positive integers a and b, there exist unique integers q and r satisfying a equal to bq plus r 0 less than or equal to r less than b. So by applying Euclid's division algorithm, we get a equal to 2q plus r for some integer q greater than or equal to 0 and r equal to 0 or r equal to 1 because here we selected b equal to 2. The value of r should be less than the value of b. So r can be 0 or r can be 1. If we give r equal to 0 here, then a equal to 2q plus 0, that is a equal to 2q. If we give r equal to 1 here, then a equal to 2q plus 1. So we got two values, a equal to 2q or a equal to 2q plus 1. We know a positive integer can be either even or odd. A number of the form 2 into q, definitely it is an even integer. If a is of the form 2q, then a is an even integer. So a equal to 2q is an even integer. Then a equal to 2q plus 1 should be an odd integer because every positive integer can be either even or odd. So we can conclude therefore any positive odd integer is of the form 2q plus 1 for some integer q. Next question is, use Euclid's division lemma to show that square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Solution. Let us apply the Euclid's division lemma. Let a be any positive integer and b equal to 3 for some integer q greater than or equal to 0, that is a equal to 3q plus r 0 less than or equal to r less than 3. A equal to any positive integer and b equal to 3. Here the form given is 3m or 3m plus 1. So we can select b equal to 3. So the possible values of r are 0, 1 and 2 because we selected b equal to 3. The value of r should be less than 3. So if we give r equal to 0, it will become 3q. If we give r equal to 1, it will become 3q plus 1. If we give r equal to 2, it will become 3q plus 2. And you see the question, it is given square of any positive integer. So we need to find out the squares of all these values. So a equal to 3q, so a square equal to 3q square. Next a square equal to 3q plus 1 whole square. Next a square equal to 3q plus 2 whole square. 3q whole square equal to 9q square. We need to change into this form 3m or 3m plus 1. So that we can write as 3 into 3q square. This 3q square we can replace as m. So we can write it is of the form 3m for some integer m where m equal to 3q square. Second 3q plus 1 whole square. This we can expand by using the identity a plus b whole square. That is equal to a square plus 2ab plus b square. So we get that is equal to 9q square plus 6q plus 1. We need to change into this form 3m plus 1. So leave that plus 1. From the remaining 2 you take 3 outside. 3 into 3q square plus 2q plus 1. So this 3q square plus 2q we can replace as m. So we get that is equal to 3m plus 1 for some integer m where m equal to 3q square plus 2q. Next 3q plus 2 whole square. This also we can expand by using the identity a plus b whole square. That is equal to a square plus 2ab plus b square. So we get 9q square plus 12q plus 4. Plus 4. We need a last plus 1. So we can change it as plus 3 plus 1. Plus 4 we can write as plus 3 plus 1. Then you leave the plus 1 last. From the remaining 3 you take 3 outside. 3 into 3q square plus 4q plus 1 plus 1. So this 3q square plus 4q plus 1 we can replace as m. So we get that is equal to 3m plus 1 for some integer m, where m equal to 3q square plus 4q plus 1. Next question is, use Euclid's division lemma to show that cube of any positive integer is either of the form 9m, 9m plus 1 or 9m plus 8 for some integer m. Solution. Let us apply the Euclid's division lemma. Let a be any positive integer and b equal to 3 for some integer q greater than or equal to 0. That is a equal to 3q plus r 0 less than or equal to r less than 3. Here the form given is 9m, 9m plus 1 or 9m plus 8. So we can select b equal to 9 or factor of 9, that is 3. Anyone we can take. Here I have taken b equal to 3. So we can write a equal to 3q plus r. The possible values of r are 0, 1 and 2. It should be less than 3. That is a equal to 3q, 3q plus 1 or 3q plus 2. The question is cube of any positive integer. So we need to find out the cube of a. That is 3q whole cube or 3q plus 1 whole cube or 3q plus 2 whole cube. 3q whole cube equal to 27q cube. That we need to change in the form 9m, 9m plus 1 or 9m plus 8. So 27q cube we can write as 9 into 3q cube. 3q cube we can replace by m. So we can write that is equal to 9m for some integer m, where m equal to 3q cube. Second one, 3q plus 1 whole cube. This we have to expand by using the identity a plus b whole cube. That is equal to a cube plus 3a square b plus 3ab square plus b cube. So by expanding we get 27q cube plus 27q square plus 9q plus 1. We need to change it to this form 9m plus 1. So you leave that plus 1 and remaining part we can consider. From that we have to take 9 outside. So 9 into 3q cube plus 3q square plus q plus 1. That is equal to 9m plus 1. We replaced this 3q cube plus 3q square plus q as m. So we can write a 9m plus 1 for some integer m, where m equal to 3q cube plus 3q square plus q. Next 3q plus 2 whole cube. That we can expand by using the same identity a plus b whole cube equal to a cube plus 3a square b plus 3ab square plus b cube. So we get 27q cube plus 54q square plus 36q plus 8. We need to change it in the form 9m plus 8. So you leave that plus 8. From the remaining you take 9 outside. 9 into 3q cube plus 6q square plus 4q plus 8. We can replace 3q cube plus 6q square plus 4q as m. So we get that is equal to 9m plus 8 for some integer m, where m equal to 3q cube plus 6q square plus 4q. Thank you.